Okay, so what we're going to talk about in the lesson today is the characteristics of sound. We're going to start with a video clip. In this video clip, you'll notice that this professor puts a bell in a vacuum inside of a bell jar and then sucks all the air out. The bell actually didn't work. He actually ended up putting a cell phone in it, but let's go ahead and take a look and watch what happens.
One of the things, that's what this was supposed to demonstrate, that without air you don't hear sound. And so the idea is you get a doorbell in here and then pull a vacuum on it. You start the doorbell ringing and then evacuate the bell jar, and then the sound disappears. Okay, and then
Alright, move closer.
I'll just pump this for a minute and then I'll close this off and shut off the motor. Okay. Nothing, right?
Can't hear the music.
Oh my God!
Okay, all right.
Okay, so what is the medium of a sound wave? Well, in this case, air would be the medium of a sound wave. So sound needs a medium in order for the wave to travel, and that would be the medium of air. And why do you not hear the sound when the sound is placed in a vacuum? There are no air particles for the sound to actually travel through. This next video clip I want you to watch. It's a short video clip of Star Wars. I want you to think about what is unrealistic about the video. Think of two things at least. As we look at the next simulation, I'd like you to think about the 6 questions that you have written down on your paper and answer them as we go. Okay, so as you're looking at this sound that's being emitted from the speaker, you will notice a couple things. There are some dark gray spots, gray lines, and there's some lighter gray lines. So we want to look at, first of all, what does the sine wave represent? So as I hover over some of these dark gray lines and lighter gray lines, you'll notice something about this pressure time graph. So this is our sine wave, and we're noticing that as the little icon is over top of the darker lines, the pressure is increasing, and as it's over top of the lighter gray lines, the pressure is decreasing. So what this is representing is the fact that these air particles are tightly compressed when the pressure is really high, and the air particles are more spread out when the pressure is lower. So the second question is, what type of wave is sound? Well, sound is a longitudinal wave. However, we can express it visually here with a pressure time graph as a sine wave. 3, what is the medium? The medium through which sound travels is air. And what is being transferred? Well, we can notice that if we look at this in terms of particles instead, we'll notice that if you spot one of these particles with the red X, it doesn't actually move from the speaker all the way to the right side. So the air particles are not actually being transferred. What's being transferred is the energy from one particle hitting another, and then that same energy being transferred to another one, and another, and another. Which property of the wave determines the volume? It would be the amplitude. So if we were to increase this amplitude, we'll notice that the waves get a lot larger. So the volume is dependent upon the amplitude. Okay, so I'm going to actually, let's see if we can hear this. Okay, so when I decrease the amplitude, the volume decreases. When I increase the amplitude, it increases. So now let's look at pitch. So I'm going to turn the sound back on and we're going to look at the pitch. So we're going to see what affects pitch. We can see that when the frequency was increased, the pitch was really high. And then when the frequency was decreased, the pitch was really low. So those points where the particles had a really high concentration, so right here on our sine wave we saw that there are high pressure, high concentration air particles. We call these points of compression. These points where the pressure is a lot lower and the air particles are not tightly bound, so we see the concentration is very low, we call that rarefaction. The pressure is lower than the equilibrium. Okay, so here's our first discussion question. For which sound, A, B, or C, would you hear the lowest volume? If you believe more than one, then go ahead and choose D. Also, I want you to go ahead and take a look at discussion question 2 right now as well, and the challenge. So discussion question 2 is for which sound would you hear the lowest pitch? And then challenge question is what is the same and what is different about sounds A and B? Let's pause the video and think about all three of those questions, DQ1, DQ2, and the challenge at the same time, and then come back to the video to check your answers. Okay, for DQ1, you should have chosen sound C as the one with the lowest volume because it has the smallest amplitude. For DQ2, you should have chosen sound A and C, both having the lowest pitch because they have the lowest frequency. Whereas sound B should have the highest pitch because it has the highest frequency. It has a greater number of waves in the same period of time. And for the challenge question, what is the same and what is different about sounds A and B? Well, sounds A and B have the same amplitude, so they'll have the same volume. Although they will have different frequencies, so they'll have different pitches. Sound B will have a higher pitch than sound A. Okay, the intensity of sound. So we can measure the volume of sound using a decibel meter. So what you're looking at on the right-hand side, the top picture is a healthy ear, and the bottom one is a not as healthy ear. So the hair follicles inside the ear, so you can see these are little hair follicles. There's not as many of them in this the lower ear canal than there is in this upper one. So how this works with the sound is sound travels in through here and it vibrates these hair follicles back and forth, which allow you to hear the sound. Well, with a great deal of loud noise through your ears over a long period of time, so if you have a high level of decibels for a long period of time over the years, you will slowly but surely lose these hair follicles and they don't grow back. So you'd want to consider this when you're listening to your music really loud. So it's acceptable to listen to or even be around sound at all at a level of 85 decibels for a total of 8 hours at a time period. That's about a little bit louder than I'm probably talking right now. Okay, so the human range for hearing is 20 to 20,000 hertz. As you get older, that range decreases. Most sensitive is 1,000 to 4,000 hertz. And if you're given time, and you guys have time left, I'd like you guys to go to this website, or the YouTube video, to take a hearing test and see what your range is for your hearing. Okay, so this next thing we're looking at is interference. So this is actually a divider, and it's placed within a what we call a ripple tank. So there's water in here, and there's two openings. So on the other side, a pebble has been dropped, and you can see that the water waves have moved significantly on both sides of the barrier. We're just going to look at this side of the barrier. So the water that moves through these openings, you can see there's points of darker points and lighter points. And so there's waves interfering with one another. And we see these darker points, we are noticing that they are constructively interfering with each other, so they have a larger amplitude. And where there are lighter regions, we can see that those represent destructive interference. So let's look at this with the simulation again in terms of our speaker and sound. So while we do this, I want you to think about the 4 questions that you have written in your notes. What do the dark areas represent? What do the light areas represent? And the 3rd and 4th one as well. Okay, so here's our second simulation for sound. We have our 2 speakers here, and we have a listener. So let's look at those questions that I asked you earlier. What do the dark areas represent physically? So these dark areas represent the crests of our sound wave, so high concentration particles, also known as points of compression if we're thinking of a longitudinal wave. The lighter areas represent our troughs, or points of low concentration of air particles, or rarefaction. So what do we hear if we have 2 sound waves that are interfering constructively? So if we have 2 sound waves interfering constructively, we should hear a larger sound or a louder sound, because constructive interference, we know, builds amplitude. So let's just take a look. So depending on where the observer is, we can see it gets quieter in some regions, and then louder in others. So we can notice that there is points where there is destructive interference and constructive interference. So what do we hear if the 2 sound waves interfere destructively? Well, if we have, let's go back for a second for constructive interference. If we have a crest, let's turn that sound off for just a minute. If we have a crest from a crest, so the dark band, and another dark band, another crest from a second speaker combining together, we have constructive interference. So we'll have a louder sound. If we have these lighter bands, so a trough, and another lighter band over here, another trough combining together, we have constructive interference as well. It'll get louder. But if we have one crest from one speaker and a trough from another speaker interfering with each other, we'll actually have destructive interference. So we should have no sound in that case. So right now we have constructive interference. Let's see. Okay, in this particular simulation, we can only see constructive interference because both speakers are emitting crests and troughs at the exact same time. So we're always going to have constructive interference. So I want you to think about which of the sound waves, when added to the source sound, will cause a listener to not hear the sound. Make sure you have an explanation as to why. So to not hear the sound. Okay, so for discussion question 3, you should have chosen sound B combined with the source sound in order for the listener to not hear the sound. And the reason why B is correct is because you can see that they are perfectly destructive interfering each other, these 2 sound waves. So at these locations where there are troughs for the source sound, there are crests on sound B. And where there are crests for the source sound, there are troughs for sound B. So perfectly destructive interference. So a real-life application of this would be noise-canceling headphones. This is exactly how they work. So in order for you to not hear anything that is going on outside of the headphone itself has a speaker, and it is able to hear the sound, the incoming sound, other than the sound that the headphones are producing. It's able to hear the incoming sound that is outside, so the external source, and then the speaker itself has another sound, and it plays a sound. And so what's created is we can see another example of destructive interference. So as a result, we don't hear anything. So there's silence. Okay. This next characteristic of sound that we're going to look at, and you're going to actually hear an example of this, is beats. So if we look at this first sound wave up here at the top, if we tried to figure out what the frequency of this wave is, we'd have to count the number of oscillations there are in 1 second. So I see 1, 2, 3, 4, 5, 6, 7, 8. There are 8 complete waves or 8 complete oscillations in 1 second. So what that means is the frequency of this first wave, F1, is 8 hertz. So for the second wave, we can see that there's one more. If we followed these little S shapes, we get 1, 2, 3, 4, 5, 6, 7, 8, and 9. So since there's 9 oscillations in that same second, F2, or the frequency of the second wave, is 9 hertz. So if we were to combine both of these sounds together and have them playing at the exact same time, the resulting sound would look something like what's below. Well, this one's a frequency of 8 hertz, and this one's a frequency of 9 hertz, so the beat is the difference between the two frequencies. So one is 8, one's 9, that means it has to have a beat frequency of 1 hertz. And we can see that based off of right here, this beat. So from here to right here, we can see it lasts negative 0.5 to 0.5, so 1 full second. So that is our beat frequency, would be 1 hertz. Let's actually go ahead and watch a short video clip on and actually hear this example of beats. Here's an example of a beat. So what you're going to hear is a tone at 440 hertz, and you'll hear another tone at 440 hertz also. So let's see what this sounds like. And then when I play the second one, you notice it gets louder since there's 2 of them playing. But let's go ahead and offset that second one by 442. And now here you're hearing the beat. You're hearing that beat twice every second. So if I increase the 442 to 443, you'll hear 3 of them every second. Because the difference between the two frequencies are 3 hertz. So the original was 440, the new one 443. So if I made this 441, you should hear 1 beat every second. And there it is. We're going to hear an example of the Doppler effect, which I'm sure you've all heard in real life before, but now we're going to actually be able to explain it. So as the video that explains what the Doppler effect is, go ahead and jot down your notes in that section that has asked for Doppler effect, that it refers to the change in blank and continues on. There's 3 bullet points there. And also go ahead and answer DQ5 and DQ6, then pause the video and check your answers.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you. And a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch.
Okay, for number 5, as a fire truck approaches the listener, what happens to its sound waves? You should have chosen C. As the source of the sound is approaching the listener, the waves get closer together and the volume is going to go up. And for number 6, if a fire alarm on the wall suddenly starts ringing, is this an example of the Doppler effect? You should have stated no. The reason why is because the source and the listener are both not moving. As for the challenge question, looks like you guys might not have that one on your piece of paper, but let's think about this challenge question. Would the sound change if you panicked and started running towards the alarm? If so, how? Well, the answer for this must be yes. If you're running towards the alarm, you're increasing the number of waves that hit your ear every second. So we're increasing the frequency of the waves. So the pitch is going to go up. Okay, so for discussion question 7, we have 3 observers, A, B, and C. They're all listening to a moving source of sound, shown in the diagram below. So let's go ahead and take a moment to pick which of the following must be true. Okay, so we should pick that 5, the frequency of the sound is highest at point C. For sure 5 is the answer because we can see that the waves are really closely packed right at point C, although at point B and point A they are not, which means our frequency must be higher here at point C. We can rule out point number 1 and 2 because we know that this is one sound, so that the speed of sound is the same through A, B, and C, because the speed of the sound must stay constant. The speed is not changing. So I'm not sure how many of you have heard of Mach 1, but Mach 1 is known as the supersonic speed, also referred to as demon in the sky. So Chuck Yeager in 1947 broke this sound barrier, so he was recognized as the demon in the sky. The X-1, the airplane that he flew at the speed of sound, which is Mach 1, was designed to resemble a .5 caliber bullet. So let's look at a little bit more about breaking the sound barrier and what this looks like. So this is called the sonic boom. So the airplane, or jet in this case, is going faster than the speed of sound, which in air it's 343 meters per second. At higher altitudes it could change. Could be a little faster. So object is creating a disturbance, travels faster than the speed of sound. So you can see that there's multiple crests that are overlapping each other, which creates constructive interference multiple times through. And as a result, we can see the sonic boom. So here's a short video clip of this actually happening. And then there's a couple discussion questions that you should complete prior to listening to the answers.
Ladies and gentlemen, the Super Hornet High Speed Pass.
Okay, so you should have had a chance to answer discussion question 8 at this point. So I want you to be able to recognize how fast the source is moving relative to the speed of sound for A, B, C, and D. So for A is the easiest to recognize. So if this were a sound source, we'll notice that it is at rest, that the object is not moving, because there are concentric circles around our source, so meaning there is no higher frequency or lower frequency at any given point. Letter C, we can see that it's traveling less than the speed of sound because the wave crests are not quite meeting each other, which means at this point there's a really high frequency and over here we have a low frequency, so the sound itself is less than the speed of sound, or the source of the sound is less than the speed of sound. And then for letter B, we can see this is exactly the speed of sound, so we would call this Mach 1 because all of the crests are meeting at the exact same point. So it's traveling at the speed of sound. And D would be faster than the speed of sound, or we could call this supersonic speed. For discussion question 9, part A, so did Chuck Yeager hear the Doppler effect from the X1's engine when he exceeded Mach 1? You should say no, he did not, because he is at the source of the sound, so he's not recognizing that it is traveling at any different of a speed than normal. But did he hear a sonic boom? You also should say no, because relative to his location, he's traveling at that same speed that the sound is also traveling at. So he's located at the source. Okay, and the last video clip just to end on a fun note.
I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
And I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint.
Choo-choo train?
Close.
A brain damaged choo-choo train?
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Well, why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect.